Now here we're going to go over the principles that I developed in the chapter 4 of postmodern winemaking that I called the 7 functions of oak. Now I probably should have called it the 7 functions of oak extractives, but let's look into barrels in general here. So what's a barrel for? Well, there are a number of things that it does. Barrels used to be like the Rubbermaid of the 19th century. So you would use barrels, you'd put crackers in them, you'd put pickles in them, you'd put nails in them. Just about anything that you wanted to ship, you would put in a barrel. And so it was really just regarded as a place to store stuff. And there wasn't a lot of discussion about flavor until recent times. One of the things that happens in barrels is settling. They have a lot of surface area and it tends to help bring things down. Turbidity can aggregate on the walls of the barrel and it can help create some lees in the bottom of the bilge. Barrels have tannin, and so they can participate in the building of structure, as we've already discussed. You get color from barrels. That's particularly important with whiskeys and brandies. And, of course, there are all of these aromas. We'll go into some depth about these a little bit later on, but barrels have all kinds of aromatics. You can also get some sweetness, depending on the nature of the toast, to round out the mouthfeel. And of course, a barrel is actually a reverse osmosis unit, a very slow one, but it does concentrate wine by breathing off alcohol and water in different ratios depending on the relative humidity in the cellar. And in any case, we lose volume and achieve concentration. Now, I think more than anything else, people buy barrels and pay a whole lot of money for them because they're interested in projecting an image. So let's look more scientifically at what happens in a barrel. To begin with, there's going to be an ullage that comes about as there's evaporation from the barrel, and the wood above that ullage is going to be drier. And so it's been demonstrated that most of the oxygen that comes into a wine barrel is coming in through this drier wood. And so there is oxidation that can happen on the surface. So then, as I said, we have evaporation of ethanol, CO2, and water. And I think I should mention also off aromas. There's a grapey sort of characteristic and some leesy aromas that will also breathe off in a barrel no matter how old it is. I find this extremely helpful in maturing a wine and off-gassing its baby fat. Then there are all these oak extractives. As I said, we'll go into quite a bit of detail there. You have some bitterness, some oaky aromas, lactones, eugenol, vanillin, guaiacol, lots of stuff. And so you have, when the barrel is new, quite a bit of these characteristics coming in. And then as the barrel gets older, you have less and less of these extractives. Now, one of the things that's really interesting in a 60-gallon barrel is that you have only a couple of feet from the bottom to the top. And so that means there's less pressure on the lees. However, we will get some reduction there. And then the reducing reactions that happen at the bottom will drift into the body of the barrel and have an opportunity to commingle and cross-react with the oxidations that are coming down from the surface of the ullage. Now, here I'm going to share quite a few slides that we got from INRA when I was working with INODEV. So thanks to Patrick Ducournau, thanks to the guys in INRA, which is a semi-governmental investigation body in France that does an awful lot of really good work. Now here is an electron micrograph of a piece of French oak, and there are several things to note here. You can see in between where the rings are is the summer growth, and there are some perforations there, and then as you see there are some quite large vessels that are perpendicular to the grain. And this is the reason why the myth of trying to avoid extraction from the end grain really doesn't work, because most of the extraction comes through these rays here, these vessels. So here's what wood is made out of. It's about half cellulose here. The rest of it is composed of lignin, and I'll show you the structure of that in a bit, versus hemicellulose units that are chains of hexoses and pentoses. And then here are the extractables, 5 or 10%, including, very importantly, the allegitannins that we'll go into. That's where we're going to get our copigmentation and antioxidative properties. Lots of volatile odor compounds, and then some fatty acids and whatnot. Now, the guys at EnoDev taught me that the bigger a wine is, the less it needs oak. Oak is really remedial, and so if you have a big wine, it really doesn't need much oak extraction. What it needs is oxygen. But small wines, like Pinot Noirs, really need the remediation of wood. And so the smaller the wine is, the more wood it takes. This is kind of the opposite of what you get taught in school, that the bigger the wine is, the more oak it can carry. And that's really a wrong-headed way of looking at it. So there are a number of words that I really don't like in winemaking. One of them is the word wine, because it combines so many different kinds of wine. You really can't talk about wine. You have to talk about specific white wine, red wine, structured wine, unstructured wine. And oak is another one of these words where it doesn't mean anything. It has been reported that the Eskimos don't need a word that means snow, because it's all snow. There's snow everywhere. You need more distinctions than that, like slush and powder and ice. And in the same way, we shouldn't say, like, I smell oak here, because there are so many different oak aromas. So you should identify the smell that you're talking about. And here's an example of the volatile compounds that you can find in wines that are derived from oak. As you see, there's quite a few. We'll get into more detail about what these are. But the whole mass taken together is the smell of oak. But there's quite a bit we can do to change the balance of these different ones depending on the way we toast or form the barrel and the origin of the wood. Now we're going to talk about the essential functions of oak extractives. So this is now a conversation outside of what a depleted barrel will give you. I don't happen to own any barrels that are less than 20 years old. I want my barrel to outlive me. And I really like neutral barrels because they give us that evaporation and that mixture of oxidation and reduction and off-gassing, baby fat, all those good things. Without oak extractors, I get my oak extractives from high-quality chips. So in talking about the 7 essential functions, the first 5 have nothing to do with aroma. And I think they're the most important. Functions 6 and 7 are curing aromatics and toast aromatics. That's what most California winemakers pay attention to. But really, the first 5 are much more important, and you really need to get it together on all those functionalities before you start thinking about aroma. So number 1 is co-extraction. We've gone into this in great detail, and we're going to use our allegitannins to help us here. So the problem is, here's an ethanol curve during fermentation, and then we've seen the total phenols have this sort of knee-shaped curve where in the early going, we're talking about monomers and skin extractives, and then in the later on, we're talking about polymers and seed extraction. The anthocyanins don't look like this at all. They go up to a point about 3 days in, and then they drop off. And that's because anthocyanins are not stable in 13% alcohol. So what do? The problem is we don't get very much pigment solubility. So what we have to do is to make incremental withdrawals from the skins and deposit them in a colloid bank. And in order to do that, we need cofactors. So anthocyanins don't like to aggregate because they have a partial positive charge and they repel each other. So we have to put some flavanols in between, so we have a kind of Dagwood sandwich, and the positive charges will coordinate with bitartrate, and we'll end up with something that looks like that. And Roger Bolton has proven that it's a 1-to-1 correspondence between monomeric anthocyanins and monomeric cofactors that does the job as a temporary holding particle until we can get at it with oxygen and tack it together into its final structure. So when we do that, we will observe that we get less precipitation of anthocyanins and we can retain them. Now, a lot of people are worried about putting untoasted oak in the fermenter because they're afraid that they're going to get plankiness. So you definitely need to work with a well-cured chip. I really like the ones from Boise France. Been using them quite a bit for many years. Plankiness that you see in poorly cured chips is coming from trans-2-nonenal. That's the kind of a smell of a lumberyard. And it goes away after about a year of curing. And then there's also syringe aldehyde, which is kind of the smell of a saw. It comes about from heating the wood when you're toasting or sawing it. So it's kind of also a lumberyard kind of smell, but not as repulsive as trans-2-nonenal. So if we get well-cured chips, we don't have to worry about plankiness. It's really quite extraordinary. So what happens during fermentation? Well, vanillin gets absorbed and degraded, but the toasty characteristics, like hydroxymethylfurfural, are amplified. Now, if you're a cheap son of a bitch and you just want to use some toasted wood in the fermenter and get more toast for your money, this will be amplified 5 or 10-fold. But I don't like to do it because it makes my wine taste like Worcestershire sauce. So I always use untoasted oak in the fermenter. And then I come in later on and maybe I'll put in a little nuance here and there to get my toast. Every wine is different and we're all learning. So you've got to run trials till you find out what works with that particular fruit from that particular vineyard. And then maybe after a course of years, you start to realize what works and you don't have to run as many trials. So that's the first function. Secondly, tannin for structuring, as I mentioned. You remember the vicinal diphenol cascade. This is a diphenol, but we've got a triphenol going for us with the elagitannins. It's called gallic acid. So these are elagitannins, and they all kind of have the same characteristics. So let's just look at this one here. And what it is a mannose. So that's a sugar right there. And it is esterified to these 5 gallic acids. You see how there's the acid group that's esterified onto this OH. And then you have this vicinal triphenol. You got 5 of those. 1, 2, 3, 4, 5 in the elagitannin. So it really isn't a tannin at all. It isn't really a polymer. And I don't know why they call it that. But when this stuff hits the pH of the wine, all these ester bonds break. So you're basically just dumping this one sugar and all of these gallic acids right into the wine. And they are wonderful copigmenters, but also have tremendous antioxidative power. Now, here we have Elagitanin degradation, what I'm trying to show you here is you don't get elagitanins in a toasted barrel. Over here is the surface of the barrel, and then as we go in 2 millimeters, 4 millimeters, 6 millimeters, now we start to get some of that stuff. And as you see, we have to go quite far into the stave before we can get these elagitanins. They're basically fried by the toast. So toasted barrels don't really give you very good elagitanins. Number 3, sweetness. Here are some of the aromatic aldehydes. Now, aldehyde, that sounds bad, but we're talking about vanillin. Vanillin is good. And coniferaldehyde is another one that's very floral. So you have all of these interesting phenolic aldehydes that give sweetness in the mouth. We can also extract polysaccharides from cellulose and hemicelluloses and other sources that can give the mouth some roundness and sweetness. So then number 4, I call framing. And here's what I mean by that. I sort of picture that the best wine has a sweet core of fruit and then kind of a box around it, some astringency, sort of like a chocolate-covered cherry. It has this rich core, then it has this framing around it from the cocoa. So there are the compounds I'm showing here that come from lignin. And then you also have acid phenols like gallic acid and syringaldehyde that come from the elagitannin, which once they oxidatively polymerize can provide some framing astringency. Number 5 is aromatic integration. Now, I'm not talking about aroma from the wood. I'm not talking about aromatic compounds from the wood. I'm talking about this idea that we keep going over of incorporating pyrazines, polyphenols, oak phenols into a structure that we're building. Oak extractives, particularly gallic acid, can help us to build a good structure so that we end up with good aromatic integration and a wine where the fruit is in the center and these other compounds play a supporting role. Now, I've shown you this before, that the tannic intensity goes up as we're structuring the wine. And then in the harmonization phase, it will come down, and this is where we want to bottle before the wine dries out. Now, the oakiness is actually at its highest when the wine is young, and it's just been put into barrel, and you have all of this extraction of oaky characteristics. But then the structure pulls those down and we get an integration of the oak aromas until the wine is falling apart, and then they come roaring out again in a wine that's over the hill. I want to talk about here the timing of lees stirring on the oak components. These will coat the tannins, sort of put pajamas on them, similar to turning dark chocolate into milk chocolate using protein from milk. However, the aromatic concentration, as I just showed you, will come down, including the fruit. So we have to think twice if we have a wine for early release about the idea that we would suppress the aroma in the wine's early years, depending on the intention for the wine itself. Now, if we have turbidity early on, it can absorb anthocyanins and degrade them enzymatically by gobbling up that glucose that's on there, particularly in Pinot Noir. And if we lose anthocyanins, then we're going to have a harder time making those short oligomers for good structure, and the result will be dryness. So as I said, we really need to get these first 5 functions right, and then we can start considering 6 and 7, curing aromatics and toast aromatic. So first of all, we have substances that come out during curing. The bois frais stuff I was talking about is cured for 2 to 3 years. And one of the things that happens, and it's facilitated microbially, is that we get a lot of lactones. And lactones are really interesting. They smell like coconut, but really they're usually kind of subliminal. And so it's a little bit in the way that a little bit of garlic will lift out the flavors of the rest of the food. Lactones will push the fruit. And so we really want to get some lactones in there. And there will be some vanillin that's created during that time. Now, I'm showing you here the characteristics of two different species of French oak, the sessile and the pedunculated. Sessile oak has a lot more volatile characteristics. So eugenol, the smell of cloves, for example, you don't have any in the pedunculated oak, and you don't have whiskey lactone. So these barrels are used for cognac because they do have a lot of tannin. And this is what you'll see in Hungarian oak and Russian oak. Anything way to the east will be predominantly pedunculated. The one thing this wood has going for it has lots of legitannins, a lot more than the sessile oaks, which are higher in vanillin, eugenol, whiskey lactone, and so forth. So that's a generality, but get a load of this. These are oaks, mostly sessile oaks from different regions of France. And you can see that they're all over the place in terms of the flavor profile that you get. So it's not just as simple as sessile versus pedunculated, although you can see that the pedunculated oaks here from the Aquitaine and from Limousin are very low in vanillin, eugenol, and whiskey lactone. So the source of the forest really matters as well. All right, now most of the aromas that we get from wood are toasted aromas. We have, for example, the aldehydes like vanillin, and then we have lots of volatile phenols that are kind of smoky. Guaiacol is a sweet smoke that's very pleasant. It's the essence of Scotch whiskey. Then we have some others that are less pleasant, like 4-methyl-guaiacol and M-cresol, which are to a certain extent associated with wildfires. Coming up next, oxygen appetite. Measuring the appetite of a wine for consuming and reacting up oxygen.